Okay, in this recording we're going to look at sigma notation and limits of finite sums. Now, just depending on what type of math class you have, classes you've had, you may or may not have seen sigma notation. So we're going to review first a little bit about sigma notation and look at how we can take the limits of these sums to find the areas of under curves, under a curve of a graph. Now, this symbol looks like kind of like a big E, is the Greek uppercase letter sigma. Okay, and when you see that sigma in math, that tells us we're going to be summing something, adding something up. Now we have an index, k, and it starts at 1 and it goes up to n. So this might be like from k equals 1 to 5, or k equals 1 to 100. And then we'll have some formula, a sub k, that tells us what the general form is for the kth term. So we would plug in 1, we'd plug in 2, we'd plug in 3, all the way up to whatever n is. Now we do just plug in the integers, so if it goes from 1 to 5, we plug in 1, 2, 3, 4, and 5. Now let's just look at some examples. This is the sum from k equals 1 to 5 of k. Now what that means is we're going to plug in 1 for k, which would be 1, plug in 2, plug in 3, plug in 4, and plug in 5. Okay, we just plug in each one of those numbers. Then we're going to add them up. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. So the value of the sum is actually 15. Okay, now let's take our next one here. Negative 1 to the k times k. Well, that means we'd plug in 1. So we would have negative 1 to the first power times 1. That's my first term, plus. Then we'd have negative 1 to the second power times 2, plus. We'd have negative 1 to the third power times 3. So we've plugged in k's of 1, 2, and 3 into this formula. Well, negative 1 to the 1 is negative 1, times 1 is negative 1. Negative 1 squared is 1. 1 times 2 is 2. Negative 1 cubed is negative 1. Negative 1 times 3 is negative 3. So I have negative 1 plus 2 minus 3. So the value of that sum is going to be negative 2. Now the next one, we only have k's of 1 and 2, from 1 to 2. So we plug in 1 over 1 plus 1. There's my first term, plus, it's a sum, 2 over 2 plus 1. Well, 1 over 2 plus 2 over 3. So we have 1/2 plus 2/3. If you find a common denominator and add there, you'll get 7/6. The last one we only do 4 and 5. So the first part we have 4 squared over 4 times 1. That's my first term. Plus, and then we plug in 5. 5 squared over 5 minus 1. Well, 4 squared is 16, and so that's 16 over 3. 5 squared is 25, so that's 25 over 4. Now, if you get a common denominator add, you're going to end up with 139 over 12 as your sum. Okay, so this big symbol just means sum. This tells you where to start, where to end, and you just plug in each integer between this starting point and this ending point and add up the terms. Now here are some rules. If we have the sum of two terms, we can just plug in our k's into the first and then into the second and add those up. Same thing for difference. Constant multiple says we can, if it were, instead of having k, it were 5k, then we could do the same, just plug in 1 through n for k, and then just multiply that answer by c. And the constant value rule tells us if we have a constant, it's just going to be n times c. And just to kind of show you how that one works, let's say we have the sum, and I don't make really good summation marks here, but the sum from 1 to 3 of 5. Well, since there's nowhere to plug the k in, our first term is 5, and our second term is 5, and our third term is 5, which gives us 15, which would just be n times c, 3 times 5, which is 15. Now here's a couple of rules that help us to be able to simplify our sums. If you sum up the first k between 1 and n, we can find that using this formula, or the first k squareds, or the first k cubes. There are special formulas for each of these. To use the top formula, let's say we want to sum the first 100 natural numbers. Okay? So we want to sum the first 100 natural numbers. Now remember, natural numbers are your counting numbers. 1, 2, 3, 4, 5, 6, 7. And so what this formula tells us is if we want to take and we want to add up from 1 to 100 of k, so that means 1 plus 2 plus 3 plus 4, ... That would be n, which is 100, times 100 plus 1 over 2. That's 100 times 101 over 2. And that would be 50 times 101, which is 5,050. So real quick and easy, I can add up the first 100 numbers just by plugging into this formula. Similarly, if you wanted to add up like 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, we could use this formula. Or 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, we could use this formula. Now we're going to come back to these in just a second because we're going to need these so we can understand how we find these limits of finite sums. Now remember this example. We took this example in a previous recording and we used left rectangles and right rectangles and mid rectangles, and we estimated the area under this. Okay? Now we're going to use this concept of limiting the value of the sums to find this area. Okay? Now we're going to think about lower sums. Okay? So remember, lower sums we took a rectangle of some certain width. We said, okay, it has this as its width, whatever its width is, times its height, and it doesn't even look like a rectangle. Sorry about that. That's not very straight there, but it's really hard to draw with this pen. But just visualize that as a rectangle. And think about what we did. Okay? Now what we want to do is we want to divide this up into n sub-intervals. Okay? If I divided it into, like, say, 10 intervals, then they would each be 1/10. Or 20 intervals, that'd each be 1/20. So each one of these intervals is going to be 1 over n. Now, the height of these intervals, okay, now we're actually, I guess we're going to use, a rectangle that starts right here at 1 over n. This point would be 1 over n, comma, f of 1 over n. Okay, so the width of each one of these is going to be 1 over n, and the height is going to be f of 1 over n. Okay, now the next one would be 1 over n, or 2 over n, f of 2 over n, and 3 over n, f of 3 over n. So however tall the next one is, it would be like 2 over n, f of 2 over n. All the way up till you get to 1. Okay? So we're going to make this a sum. What we're doing here is we're adding up, starting at 1, and we're going all the way up to n. n over n would be 1. Okay? And the width of these rectangles are 1 over n, times the heights of these rectangles, f of k over n. Now the reason I'm using k over n is because this function value is changing as we make each of our rectangles. It starts out as 1 over n, then 2 over n, and 3 over n, and 4 over n, and 5 over n, all the way up to n over n, which is 1. Okay? Now, that means what we've got here is the sum from 1 to n of 1 over n times f of k over n. Now, f of k over n is going to be 1 minus k over n squared, because it's 1 minus x squared. So we're just going to plug in k over n. So that gives us the sum from k equals 1 to n of 1 over n times 1 minus k squared on top, n squared on bottom. Then I'm going to just distribute my 1 over n. So this is the sum from 1 to n of 1 over n times 1 is 1 over n, minus 1 over n times k squared over n squared is k squared over n cubed. Okay? Now I'm going to apply some of those formulas that we had earlier. First off, we can split them apart. This is the sum from 1 to n of 1 over n minus the sum from 1 to n of k squared over n cubed. Now remember, the n is some known value. It's not a variable. Okay, so we could make n, if we want to do 5 rectangles, we'd make it 5, or if we want to do 50 rectangles, we'd make it 50, and so forth. Okay, so let's look at what we do. This here is just a constant. Okay, so remember, the rule for a constant was, if you have some constant, it's just n times that constant. That means this is just going to be n times 1 over n. And that will be this first sum, because what we're going to be doing is, say that n is 5, we're going to be doing 1/5 plus 1/5 plus 1/5 plus 1/5, 5 times. Now, we can also use that constant multiple rule. This is k squared times 1 over n cubed, and it said that we could bring the constant out to the front. So that would be 1 over n cubed times the sum, that should be k there, from 1 to n of k squared. Well, this n minus 1 is 1 minus n cubed times, now we're looking at the the sum from 1 to n of k squared. Well, we've already got that formula. This is the formula that we have right here. N times n plus 1 times 2n plus 1 over 6. Now notice I don't have any sum symbols anymore. I've eliminated my sums. I've used the constant rule, the constant multiple rule, and the rule for the sum of squared terms. This will give me 1 minus n times n plus 1 times 2n plus 1 over 6n cubed. Now, we don't really have time to do all the algebra here, but if you will distribute out what you've got on the top, distribute the n and then FOIL, you'll have 1 minus, and on top you'll have 2n cubed plus 3n squared plus n over 6n cubed. And again, you'll get that if you'll just FOIL, or distribute n times 1, and then just FOIL out your numerator. Now what we want to look at is what happens as n gets larger and larger and larger. So we saw as we got more and more and more rectangles that this got closer and closer and closer to a limit. And so what we want to do is we want to take the limit of this sum. Okay, so we're going to take the limit as n approaches infinity of 1 minus 2n cubed plus 3n squared plus n over 6n cubed. Now remember back to the rules for limits, and you'll remember that what we did when we had variables like this and rationals is we went through and we divided everything by, of course we're taking the limit of this whole thing, so I probably need to put parentheses or brackets around it. We divided everything by n cubed. If I go through and divide everything through by n cubed, 2n cubed divided by n cubed would be 2. Plus 3n squared divided by n cubed would be 3 over n. Plus n divided by n cubed would be 1 over n squared. And 6n cubed divided by n cubed would be 6. Okay? Now, if as n goes to infinity, 1 is just 1. And this is going to be 2 plus, remember as n gets larger and larger, this gets close to 0, this gets close to 0. This is going to be 1 minus 2 6, and 2 6 is 1/3. 1 minus 1/3 is 2/3. Okay? The actual area under this graph is 2/3. And if you think back to the previous recording when we were doing rectangles and it showed, if you did like 1,000 rectangles, then it was 0.6666, went out a few sixes before it changed values. This is this is actually 2/3. And what you got when you got larger and larger and larger numbers of rectangles was very, very close to 2/3. Okay? Now here's just a typical continuous function over a closed interval. Now notice part of this is below the axis and part of this is above the axis. what we'd have to do is we'd have to do rectangles below and rectangles above. Okay, so if we were finding the area, we'd actually be finding this area and this area, the area between the graph and the x-axis, so this area and this area. So we'd need to do finer and finer partitions of rectangles. Okay, make smaller and smaller and smaller rectangles to get closer and closer and closer to the actual areas.